Section 8.2, Distribution of the Sample Proportion. We'll look at these two objectives in this section. Objective 1. Describe the sampling distribution of a sample proportion. First, let's look at a point estimate of a population proportion. Suppose that a random sample of size n is obtained from a population in which each individual either does or does not have a certain characteristic. The sample proportion, denoted p hat, is given by this formula here. P hat will be x divided by n, where x is the number of individuals in the sample with a specified characteristic. The sample proportion p hat is a statistic that estimates the population proportion p. Let's look at this example, computing a sample proportion. In a university poll conducted in May of 2008, 1,745 registered voters nationwide were asked whether they approved of the way George W. Bush is handling the economy. 349 responded yes. Obtain a point estimate for the proportion of registered voters who approve of the way George W. Bush is handling the economy. So remember, our point estimate is our value p hat, which is given as x divided by n. So x would be the number who responded yes, so we have 349, where n then is the total who were asked, or the registered voters, which would be 1,745. And when we do this division, we'll get a value of 0.2 for our point estimate. So this is a point estimate for the proportion of registered voters who approve of the way George W. Bush is handling the economy. Now let's look at another example using simulation to describe the distribution of the sample proportion. Based on a study conducted by the Gallup organization, 76% of Americans believe that the state of moral values in the United States is getting worse. Describe the sampling distribution of the sample proportion for samples of size n equal 10, n equal 25, and n equals 60. Note, we are using simulations to create the histograms on the following slides. Figure A shows a histogram of 2,000 sample proportions from samples of size n equal 10. Notice that the shape of the distribution is skewed left. The mean is 0.76 and the standard deviation is 0.136. Notice that the mean of the sample proportion equals the population proportion. Figure B shows the histogram for 2,000 sample proportion from samples of size n equal 20. Notice that the histogram is only slightly skewed left, although not as skewed as the histogram with n equal 10. The mean is 0.76 and the standard deviation is 0.096. Figure C shows the histogram for 2,000 sample proportions from samples of size n equals 60. Notice that this one is now approximately normal, with a mean of 0.76 and a standard deviation of 0.054. So here are some key points from that example. For the shape, as the size of the sample n increases, the shape of the sampling distribution of the sample proportion becomes approximately normal. The center, the mean of the sampling distribution of the sample proportion equals the population proportion p. And the spread, the standard deviation of the sampling distribution of the sample proportion, decreases as the sample size n increases. So let's look at the sampling distribution of p hat. For a simple random sample of size n with population proportion p, the shape of the sampling distribution of p hat is approximately normal provided that n times p times 1 minus p is greater than or equal to 10. The mean of the sampling distribution of p hat is mu sub p hat, and it's equal to p, the population proportion. The standard deviation of the sampling distribution of p hat is given by sigma with a subscript of p hat, and it's equal to the square root of p times 1 minus p divided by n. The model on the previous slide requires that the sampled values are independent. When sampling from finite populations, this assumption is verified by checking that the sample size n is no more than 5% of the population size capital N. So little n must be less than or equal to 0.05 times capital N. Regardless of whether n times p times 1 minus p is greater than or equal to 10 or not, the mean of the sampling distribution of p hat is p, and the standard deviation is the square root of p times 1 minus p over n. So let's look at this example describing the sampling distribution of the sample proportion. Based on a study conducted by Gallup organization, 76% of Americans believe that the state of moral values in the United States is getting worse. Suppose we obtain a simple random sample of size n equals 60 Americans and determine which believe that the state of the moral values in the United States is getting worse. Describe the sampling distribution of the sample proportion for Americans with this belief. The sample of n equals 60 is smaller than 5% of the population size, which would be all registered voters in the U.S., which is somewhere in the billions. So it's definitely less than 5%. Also, n times p times 1 minus p would be 60 times 0.76 times 0.24, which is 10.944, and that is greater than or equal to 10. So now the sampling distribution of the sample proportion is therefore approximately normal with a mean of 0.76 and a standard deviation equal to the square root of 0.76 times 1 minus 0.76 divided by 60. And this will give us a value of 0.055. Note that this is very close to the standard deviation of 0.054, which we found using simulation in example 2. Objective 2. Compute probabilities of a sample proportion. In this example, we'll compute probabilities of a sample proportion. According to the Centers for Disease Control and Prevention, 18.8% of school-aged children aged 6 to 11 years were overweight in 2004. In a random sample of 90 school-aged children aged 6 to 11 years, what is the probability that at least 19% are overweight? First, we see that n equal 90 is less than 5% of the population size, which would be all school-aged children aged 6 to 11 years. Then n times p times 1 minus p would be equal to 90 times 0.188 times 1 minus 0.188. This would give us a value of about 13.7, and that is greater than or equal to 10. So that means that p hat is approximately normal with a mean equal to p, which is equal to 0.188, and a standard deviation equal to the square root of 0.188 times 1 minus 0.188 divided by 90. And this will give us about 0.0412. So let's convert this to a z-score. We want to know the probability that at least 19% are overweight. So we have 0.19 minus the mean, which was 0.188, divided by the standard deviation we just calculated, which was 0.0412. And we get a value of 0.0485, which is approximately 0.05 for our z-value. So we're looking at then the probability that z, if it's at least 19% or at least 0.05, then it is greater than or equal to 0.05. So we'll take 1 minus the value when we look it up in the table, which is 0.5199, and we get a value of 0.4801. And this would be the probability that at least 19% are overweight. In B, suppose a random sample of 90 school-aged children aged 6 to 11 years results in 24 overweight children. What might you conclude? So P hat is equal to 24 out of our 90 children, or 0.2667. And remember that we calculated previously our mean of P hat was equal to 0.188, and our standard deviation for P hat was 0.0412. So let's use our z-score for P hat, and we'll take P hat, which we found to be 0.2667, minus the mean, which is 0.188, divided by the standard deviation of 0.0412, and we'll get approximately 1.91. So the probability then that z is greater than 1.91 will be equal to 1 minus that value from the table, which is 0.9719, which is equal to 0.028. We would only expect to see about 3 samples in 100, resulting in a sample proportion of 0.2667 or more. This is an unusual sample if the true population proportion is 0.188.